I've done a couple videos on the half Atwood machine. So the half Atwood machine, you have a mass, hopefully low friction, and it's on a horizontal track with a pulley right here connected to another mass. You let it go and it accelerates. And that's a pretty cool problem. And I'm going to actually do this one. But I saw a version of it that looked like this. I had terrible drawing, I know. But the idea is that there's a mass, a pulley, and a second pulley down here. So the string goes over the pulley, down to this pulley, up and back up to that pulley. And then, so what's going to happen in this case? And wait, I'm going to show you a video. I actually made this just to show you that it actually is real. And then I'm going to solve this problem. Then I'm going to solve this problem. I'm going to find the acceleration for both. Okay, so here is the video I made. So here's the cart. Here's the pulley. There's a second pulley. I'm just going to scroll through it because I actually pushed it. I pushed it going up so that you could see it. And there's a tiny little mass on the end of that. And so there it goes. Pretty cool, huh? I guess I should play it in real time. Nice. Okay. So like I said, I think it'd be a good idea to first redo the half Atwood machine. There's a couple ways to solve this, but I'm going to solve it the best way. I mean, the most thorough way. So I'm going to draw a free body diagram for mass 1. There's no friction here. M1G, gravitational force, N, I'll just call it N. And then I have a tension right here, like that. For mass 2, I have M2G and the tension. Now, the weight on this one has to be greater than the tension, because this has to accelerate that way. Okay. So let's, in this case, the only thing that matters is the tension, right? Because if I use Newton's second law in the y direction here, the forces add up to 0 because there's no big deal. It doesn't accelerate, so it's stupid. It's not stupid. It's just not that cool. I guess that'd be stupid. So I just have this tension right here. So let's write the x equation for this one. This one's going to accelerate that way. Whether it's moving this way or that doesn't matter. It's accelerating that way. So I'm going to say F net x is going to be t in the positive x direction, and that's going to be equal to m1a. Okay, now I'm going to switch over here in the y direction. What's important about this situation is that since these have the same string, then this magnitude of tension has to be that magnitude of tension. And the magnitude of acceleration for this has to be the magnitude of acceleration that. If it wasn't, then the string would stretch and break or whatever. So for this one, I'm going to say that's the negative y direction. I'm going to say F net y is going to be t minus m2g. That's the y component of the gravitational force right there. Is going to be equal to minus m2a. So what I have here is two equations, two unknowns. I just need to solve. So I already have this one for solve for tension. I'm going to go ahead and plug tension in down here, and I'm going to, as m1a, I get m1a minus m2g equals negative m2a. And I want to solve for a, so I'm going to add m2a to both sides. I'm going to add m2g to both sides. I get m1a plus m2a equals m2g. Now I can factor out the a times m1 plus m2 equals m2g. So a is going to be equal to m2g over m1 plus m2. And that's my acceleration. Now, it's important to realize that the other way to do this is to think of the whole system of these two things. And in that case, the force that makes it accelerate is just the weight, right? Because the tension's an internal force. And so the force accelerating the system's m2g, but everything has to accelerate. So the total mass accelerating is m1 plus m2. And so here's mass times acceleration, and that's force. And you solve for a. Cool. Okay, now, what do you think? What do you think will happen if I put this pulley? Do you think you'll have a greater acceleration or a lower acceleration? Well, let's just do the same thing. Let's draw the free body diagram. So I'm going to draw a little bit bigger so I can make a better picture. So here I have a pulley, and here I have another pulley. I'm going backwards. And that's connected, and this goes down and up that. Okay. So this is again M1, M2. So the force diagram for M1 is the same. M1G, N, that's a G, T. So I still get F net X is going to be equal to T, and that's going to be equal to M1A. This one's going to accelerate that way. This one's going to accelerate down. Now let's draw the free body diagram for M2. I'm going to draw it off to the side right here. I'm going to draw it right here. So I have M2G pulling down. And then what's pulling up? Well, you could say, I'm going to include this pulley as part of the mass. And in that case, if I do look at this, you'll notice that there are two strings attached. So this string pulls up with a tension T. That string pulls up with a... Strings can only pull, so they have to pull up. So I have T and T. There's two of them. And this is the key to pulleys. Okay. So for this one, I could say F net Y is going to be equal to 2T, right? There's two of these, minus M2G, and that's going to equal negative M2A. So you can see we have a very similar idea. I can go ahead again, substitute this into T. I already have that solved. So I get 2 times M1A minus M2G equals negative M2A. Now I want to add this to both sides, so add that to both sides. I get 2 M1A plus M2A equals M2G. Factor out the A times 2 M1 plus M2 equals M2G. Divide both sides by that. A is going to be M2G over 2 M1 plus M2. Okay, so is this greater than or less than the other acceleration? The answer is, well, since I'm going to have a larger number on the bottom because I have 2 M1 plus M2, then it will be larger. I mean, smaller. Sorry. Smaller, a lower acceleration. Let's check a couple other things. What would happen if this mass gets really, really, really small? Then this would essentially fall, free fall. Okay, so if as M1 goes to 0, then I get M2G over M2. I get an acceleration of G, which I've already determined the direction. Don't think, oh, you got the direction wrong. I've already said the direction is down. What if M2 is very small? If that's very small, then that's very small. I get an acceleration of approximately 0. So that's good. The units are fine and everything. So that's good. So that's the answer. But it seems like it's not fair, right? It seems like something isn't quite right. And that's because you have a lower acceleration, but the same masses. How can everything be fine? Well, the answer is that energy is still conserved. Because every time this moves down, then this is going to have a smaller acceleration. This doesn't move as far, right? Because if this moves down, let's say a meter, well, then this is going to move further. Let's see. If this moves down a distance s, then this string has to, both these strings have to, then this will move half s, right? Because both of these strings will have to, this string will have to move down. Yeah, but some of it goes up. Yeah, so that's right. Okay, so with that, we can use the work energy principle just to see if energy is still conserved. So let's use the work energy principle for the first Atwood machine. And we're not going to find the acceleration, although you could. So let's let this fall a distance s. In that case, I'm going to say my system are my masses, both of them, plus the Earth. Using the work energy principle, I can say work is the change in energy. In that case, it's going to be the change in kinetic energy plus the change in gravitational potential energy. And there's no work done on my system. The normal force is exerted on this, pushing up, but it doesn't do any work because the displacement's this way and the force is that way. So that's zero work. So I get 0 equals the change in kinetic energy. Let's call this position 1 and down here position 2. So it's going to be 1/2 m1 plus m2 v2 squared minus 1/2 m1 plus m2 v1 squared. That's my change in kinetic energy. I have to include both masses because both masses change speed. Plus the final, let's call this y equals 0. So y1 equals 0, y2 is negative s. So the final potential energy is going to be equal to minus m2gs. This one didn't change any, it didn't move up or down, just that mass did. And then minus the initial potential energy, which is 0 because it started up there. So now I can solve this. I want to solve this for V2. If it starts from rest, V1 is 0. So I get 1/2 m1 plus m2 v2 squared. I'm going to add that to the other side is m2gs. So v2 squared is 2 m2gs over m1 plus m2. So v2 is the square root of 2 m2gs over m1 plus m2. So let's just check. That has units of, this is units of energy divided by, so that'd be joules. Let's see, a meter, that's a joule per kilogram. Is that a meter per second? See, a joule is a kilogram, meter per second, meter squared per second squared. So the kilograms cancel, I get meters per second. Okay, that's right. So now let's do the same thing for the half Atwood machine. I'm going to not draw the pulleys because it just, well, it will. So if this falls down a distance s, then this is going to move a distance s over 2. But they don't have to have the same speed now, right? They don't have to have the same speed. And in fact, I kind of skipped over some stuff here, and I wish I wouldn't have even done this. But how do you find the relative speeds? You actually have to take derivatives. Okay, I'm not going to finish the problem, because I was doing this as an algebra-based problem. I guess I could calculate the tension. That'd be kind of fun. I could calculate the tension and then use that. I am going to do it. I'm not going to back down. So let's go back up here. That's my acceleration. I can find my tension. So let's write down the tension. T equals M1A, and A is going to be equal, so it's going to be M1 times M2G. I put those backwards because I was thinking, divided by 2m1 plus m2, 2m1 plus m2. So that's the tension in my string. If I know the tension and I know the displacement, I can find the final velocity of this, which I don't actually, I want to find the velocity of this compared to that. And in fact, I don't have to do the work energy for the whole thing. So now I'm going to say my system is just mass 1. So in that case, I have work is the change in kinetic energy. There's no potential energy, right? Because it doesn't move up or down. But there is work. Work equals T dot delta R. In this case, that's just going to be TS over 2. Because it moves the distance S over 2. The tension is in the same direction as displacement. So it's just going to be the product of their magnitude to those two vectors. So I get TS over 2. That's the work. And that's going to be equal to the change in kinetic energy. And I want to compare that to this value right here. So if that's the case, I can say TS over 2 is 1/2 M1 v2 squared minus 1/2 m2 m1 v1 squared. Now the initial velocity is 0, so if I solve this for v2, I get v2. I'm going to multiply both sides by 2. They cancel. Divide by m. It's going to be the square root of ts over m1. But you'll notice up here, t, if I put in for t this, I get the square root, the mass 1 cancels. I get m2g over s over 2 m1 plus m2. And you'll notice that this velocity it's very similar to that one, but it's going to be smaller. Why do I have a 2 right there? Yeah, that's weird. I have a 2 there. Okay, it went half the distance. Yeah. So it's not just... So it's definitely going slower. And that's fine because this one would be going... I could calculate that speed too. That one's going to be going faster than this one because it moved a further distance. So if it has the same time, but twice the distance, it's going to be going twice the speed. So this will be going twice the speed of that one. Okay, I think I kind of messed up on the end, made it a little confusing, but I think it's still a great problem, and I had fun.